This video will be a demonstration of an example dataset where heteroscedasticity is obviously present in the data, which is in contrast to the original example where heteroscedasticity wasn't present, and so you could make an argument that you can trust the normal theory p-value in the analysis. So in this case here, the first way I'm going to look at this issue is to look at the more of an art than a science approach. So first I'm going to conduct a regression, linear, and I'm going to put education as the independent variable and income per day as the dependent variable. And I'm going to have plots here. And I want to look at Z_predict as the independent variable and Z_residual as the dependent variable, the y-axis, and click OK. And here we get the scatter plot. If you're trying to get some sense of heteroscedasticity in this plot, good luck to you. I don't think it's really that obvious. And that's why I recommend in the textbook that you should create standardized residuals that are absolute in nature. So in order to do that, click Analyze, Regression, Linear. And in this case, I want to save the standardized residuals and the standardized predicted values. And click Continue, click OK. And now I want to create absolute values out of the residuals. And I've done this before, so I'm doing this again on this data set. And I'm assuming you've seen me do this before. So ZRE1 absolute, and I'm going to get the absolute function and put the residuals in there. Click OK. And now I'm going to create a scatter plot out of that variable with the Z_predict on the x-axis and Z_1 absolute on the y-axis. So click on Graphs, Scatter, and put the ZR1 absolute variable on the y-axis and the Z_predict on the x-axis. Click OK. So in this case here, I'm starting to see some kind of pattern. It looks like there's a positive correlation going on in these data. In fact, with the simplest and arguably certainly respectable approach to testing the assumption of homoscedasticity, you could just run a correlation between the predicted value and the absolute value. Looking at this scatter plot, I can see a pattern of a positive correlation. So let's actually verify that to be the case. Predicted value in there, absolute value in here, and I want Pearson and Spearman. And we can see that I do get clearly a statistically significant correlation between the predicted values and the absolute residuals, which means that as the predicted value increases, the amount of error in the prediction of the dependent variable earnings is getting worse. So the regression equation, which is saying that the intercept is -48 with an upward slope of $9.95 a day and a standardized beta weight of 0.393, this positive correlation is saying that the regression equation is breaking down progressively as predicted values increase. So that's a problem. That's a problem that the regression equation is creating bigger residuals at the higher end of the predicted value, which means basically that as education increases, the regression equation's ability to predict earnings decreasing. It's getting worse and worse. So this is a problem for the analysis. You could also use the co-anchor test, which I described in a previous example, how to input this. So check out the video relevant to Ahmad Daryanto's macro that you can install into SPSS to run the co-anchor test in an efficient way. So in this case, I just need to put my outcome variable, which is income per day here, and education as my explanatory variable, and click OK. And we can see that, again, I'm going through this quickly because I've done this before. This is just a rehash of the bivariate regression. We got that in SPSS already. And here is the co-anchor test, which is statistically significant. I mentioned before that the co-anchor test is a more valid test than the Broich-Pagan. The co-anchor is an extension of the Broich-Pagan test and overall is a better test. And we can see here that this p less than 0.05, in fact p equal 0.019, is corroborating the statistically significant correlation between the predicted values and the absolute predicted values. So in this example, the assumption of homoscedasticity has been violated. It's apparent in the graph where I can kind of see an upward slope and kind of a pattern here, supported by the correlations that are statistically significant between the predicted values and the absolute residuals, and it's also corroborated by the Coanker test. So now you would have to apply some kind of correction to the standard errors in the regular bivariate regression, because I can't trust this standard error anymore. And that's where in the next video I'll show you how to do the heteroscedastic corrected standard errors by the Hayes and Kai method, which I showed in a previous video before as well.